Okay guys, these are the notes for section 9B. I'm on pages 6 and 7 of the note packet. If I'm speaking too slow, feel free to click on that gear wheel and speed up the video on YouTube. So in this section we're going to talk about sample spaces, and first to define it, a sample space is a set of all possible outcomes of an experiment. It's also referred to as a universal set if we bring back some language from the sets chapter. You're going to eventually see 5 ways to come up with a list of all possible outcomes. So we might just list it out from essentially the top of our head, making just some common sense lists. 2-dimensional grids, tree diagrams. So you'll see those 3 things in this section, and tables of outcomes and Venn diagrams are in another section. So the first 3 things. Listing outcomes. If we just give you an example of what we mean by listing outcomes, if you toss a coin, just a coin, the sample space would just be curly brackets, H, T, a list of outcomes. Rolling a die, a single die, assuming there are 6 sides, the sample space is simply the list. Okay, so we're just coming up with that list from the top of our heads because it makes sense. Okay, if things get a little bit more complicated, then 2-dimensional grids can come in handy. And if the experiment involves 2 operations, we can make a grid of outcomes. So for example, suppose we flip coin 1 and coin 2. So if we flip coin 1 and coin 2, we can make a grid, meaning an X and a Y axis, with the labels H and T for coin 1, H and T for coin 2, and then you can realize that 4 possible things can happen. Reading these dots that I just made in the grid, we can get HH, HT, TH, and TT. Notice that HT, TH, I realize that they are both outcomes where there's one head and one tail, but they are considered different outcomes. So heads on the first coin, tails on the second is different from tails on the first and heads on the second. So knowing those 4 possible outcomes in the sample space for flipping 2 coins, once we get into some probability rules, it will be important to know that there are those 4 outcomes. All right, next we have tree diagrams. So if we prefer what we just talked about in example 3, okay, so tree diagrams. Here we go. If we toss 2 coins, what we want to do is we just want to make a dot on the left and start drawing branches. Now we'd only need 2 because coin 1 could either be H or T. And then from the H on coin 1, we could follow that up with an H or a T on coin 2, or follow it up a tail with an H or a T on coin 2. So we ultimately can read the branches to know that this set of branches produces the outcome HH, this one HT, this one the TH, and this one the TT. Once again, seeing 4 possible outcomes. If we have marbles and we draw a bag for marbles that are red, green, or yellow, well, marble 1 could be red, green, or yellow. So if we start with a dot on the very left, there would be 3 branches with red, green, or yellow. And then following the first marble, we could follow up with marble 2, a red, green, yellow, following the first green, red, green, yellow, following the first yellow, red, green, yellow, producing this list of outcomes. Okay, now for tree diagrams, there are some students who mistakenly go out and do this. They say, oh, well, coin 1 could be H or T, and coin 2 could be H or T. That's not a proper tree diagram. A proper tree diagram would show all possible combinations of what could happen on coin 1 and coin 2, not separately displaying coin 1 versus coin 2. So I kind of jokingly say, well, you drew just 2 little bushes instead of drawing a tree. Flip into page 7 to do some examples showing those 3 things. Okay, what if we twirl a square spinner labeled A, B, C, D? What does it look like to just make a list? So the sample space S would simply be a list, A, comma, B, comma, C, comma, D, because that's what could happen if we twirl a spinner. The sex is in a two-child family. This, again, off the top of our head, a two-child family could have boy then another boy, boy then a girl, girl then a boy, or girl, girl. So you see here, we have something that looks very similar to just heads and tails. All right, let's try the grid. If we roll a die and toss a coin, and we have to make a grid. So a grid has two axes. Let's put the die here and the coin here. The coin's going to either be an H or a T, and the die is going to be a 1, 2, 3, 4, 5, 6. That's going to produce 12 dots in the grid, and every one of those dots represents an outcome in this chance process. So if I have to make the sample space, that's the illustration, but if I had to list it out, I could write one with tail, one with, let me go, well, since it really just said make the illustration, I'm not going to bother with the list. Okay. Part B, if I roll 2 dice, well, now my grid's just a little bit larger because I'll need an axis for die 1, we'll need an axis for die 2, and we need the numbers 1 to 6 on each one. So you see here, by the time I fill this grid in, I'm going to have 6 dots 6 separate times, so we'd have 36 outcomes in this 2 dice sample space. Again, notice that when I make a dot at the 5, 1, it's different than this dot over here at 1, 5. These are different outcomes. I realize they would both have a sum of 6, but that's not relevant. They are different outcomes. All right, and then the third example, a tree diagram for a coin toss where we have a nickel and a dime. Okay, so the tree diagram, nickel, dime, part A. So remember, 1 dot on the left. Here's me flipping the nickel. The nickel could land on heads, tails. All right, and then I have a dime. So the dime could be heads, tails as well. And that's the tree diagram. Part B, what if we toss a coin and twirl an equilateral triangular spinner with ABC on it? All right, here's the coin, HT, and then I follow that up with a spin. That could be A, B, or C. Okay, those are called tree diagrams in probability. Okay, that's section 9B.